Last time, we developed the basics of L2 theory, and in particular, the notions of covariance and correlation. In this lecture, we're going to use those to prove one of the first big limit theorems in probability theory, the weak law of large numbers. Before we get there, we need to revisit one of the key concentration inequalities from measure theory, Markov's inequality, which tells us that for a non-negative random variable, the measure of the set where it exceeds some threshold epsilon can be bounded above by its pth integral, divided by that threshold to the power p, for any positive number p. It's common to call this Markov's inequality usually when p is equal to 1, but let's consider the case where p is equal to 2 and apply it in a special case. Let's work with a probability measure now, and suppose that our measurable function, that is a random variable, is actually in L2. That is, we will take p equal to 2 in Markov's inequality. And we will apply Markov's inequality to the non-negative measurable function, which is the absolute value of the centered version of x. That is, again, the absolute value of x minus its expectation, which is finite because x is in L2. Then Markov's inequality, as above, tells us that the measure, the probability, of the set where the absolute value of centered x is greater than or equal to epsilon is less than or equal to 1 over epsilon squared times the expected value of the square of the centered version of x. But the expected value of the square of the centered version of x is the definition of the variance of x. And so what this inequality tells us is that the probability that x minus its expected value is bigger than or equal to some threshold epsilon is less than or equal to 1 over epsilon squared times the variance of that L2 random variable. In this form, we call the inequality Chebyshev's inequality. It is one of the most commonly used concentration inequalities, and what's useful about it is that it is centered not at the arbitrary point 0, but at the expected value of the random variable. It tells us that the random variable, assumed to be in L2, does not stray very far from its expected value. As we move farther and farther away from the expected value, the probability that it spends time there falls off as a quadratic function of the tolerance epsilon, weighted by this fixed finite number, the variance. There's an alternate way to write this by rewriting the tolerance epsilon. Let's introduce the notation sigma, not sigma field, but sigma of x, to be the square root of the variance. That's the standard deviation of the random variable x. Then in Chebyshev's inequality, if we substitute epsilon is equal to some positive number k times the standard deviation of x, what Chebyshev's inequality says is that the probability that centered x in absolute value exceeds k times the standard deviation of x is less than or equal to the variance of x divided by k times the standard deviation of x squared. But the standard deviation of x squared is the variance of x, so that's just 1 over k squared. And so what this says is that the probability that x deviates from its expected value by at least k standard deviations decays at least as fast as 1 over k squared. That doesn't tell us much if k is less than 1, but already with k equal 2, it says that a random variable being at least 2 standard deviations away from its mean has probability less than or equal to 1/4. Now, that's a worst case scenario. In most random variables, like a normal random variable, the bound falls off much faster. For normal random variables, this 1 over k squared can be replaced with an e to the minus constant times k squared, a much faster decay rate. But this is universal for all L2 random variables. And in particular, we're going to use it to see a concentration result about large averages. What does expectation really mean? We've defined it as a weighted average But what is the motivation for this weighted average to be a statistic we consider? To motivate this answer, let's go to our favorite probabilistic example, tossing a fair coin repeatedly. We can, as usual, model this with a sample space consisting of all sequences of 1s and 0s of length n, where n is the number of tosses. 1 means heads, 0 means tails. We'll work with the sigma field of all subsets and use the uniform discrete probability measure, which assigns to each outcome the probability 1 over 2 to the n. That is, it assigns equal probability to all outcomes. Then what we're interested in here are the random variables xj, where xj of the sequence omega equals omega j, the 0 or 1 in the jth position of that sequence. This random variable tells us whether the jth toss is a heads or a tails. Now we can compute the expectation here as we've done. Let's do it again, right from first principles. The expected value of xj is, by definition, the sum over the entire sample space of the value of xj, which is omega j, times the probability of xj, which is 2 to the minus n. Now, we could write out this sum, but really all we have to do is note that omega j equals 0 half the time. It equals 0 in 2 to the n minus 1 outcomes, and omega j equals 1 in the other 2 to the n minus 1 outcomes. And therefore, half of the terms in this sum of 2 to the n will be 1, and half will be 0, which means that this expectation will equal 1/2. But what does it mean that that expectation will equal 1/2? Well, let's count how many heads come up all together. That's the sum of x1, x2, up to xn. We'll call that random variable Sn, the sum. And so we can write it explicitly. Sn of the sequence omega is just the sum of the terms in that sequence. This is a random variable. What are its possible values? What is the state space for this random variable? Well, it could take value 0, or 1, or 2, all the way up to n. An integer between 0 and n. What is the distribution of the random variable Sn? Well, it's a discrete random variable. Its distribution is a probability measure on the finite set from 0 up to n. And so we just have to specify the probability of each value. So the probability that Sn takes the value k, for k being an integer between 0 and n, is exactly, because of the uniformity of the probability measure, the number of outcomes, omega, for which the sum of them is k, divided by 2 to the n. Well, that's relatively easy to count. How many sequences of 0s and 1s have exactly k 1s? It's just a matter of choosing the k positions for the 1s among the total n positions. And that is counted by n choose k. And so this probability is given by 1 over 2 to the n choose k. Now that probability distribution has a name. It's called the binomial distribution, with parameters n and 1/2. 1/2 here for the probability of any coin toss coming up heads or tails. What's the expected value of this random variable Sn with a binomial distribution? We could compute it combinatorially from this distribution of values, but it's better to note that Sn is a sum, and therefore the expected value of Sn is the sum of the expected values of the xn's. Now, each of those xj's has expectation equal to 1/2, and so Sn has expected value n over 2. All right, so we know the expected value. We actually have the whole distribution, but that still doesn't really tell us, philosophically, what the expected value means. Well, instead of the number of heads, let's look at the proportion of heads that come up. That is, Sn divided by the total number of coin tosses, n. the empirical average of the x's. Now that random variable has expected value equal to 1/2, since expectation is linear and the expected value of Sn is n halves. What we'd like to see is what that number 1/2 means in this context. It doesn't just mean the expected value. In fact, we'll see that the random variable Sn over n concentrates pretty heavily near the point 1/2 as n grows. How do we see that? Well, let's consider the probability that Sn over n, the proportion of heads, minus the average, the expected value, 1/2, is bigger than or equal to some tolerance epsilon. One nice thing we can do is use Chebyshev's inequality and estimate this probability from above by the variance of Sn over n divided by epsilon squared. Now, if epsilon is very small, that means the denominator is even smaller, and so this is a big number, but we're holding epsilon fixed and considering what happens as n grows. One thing we'll note right away is that since the variance is a quadratic function, that 1 over n can be pulled out as a 1 over n squared. And so we just need to see what happens to the variance of Sn. Of course, just because there's an n squared in the bottom, there's an n-dependent quantity in the top, and this doesn't tell us a lot on its own. So what can we say about the variance of the sum? Well, for the time being, I'm just going to refer to the distribution of the random variable Sn, the binomial distribution. So we could compute this, in principle exactly, by definition. The variance is the second moment, which from the change of variables formula is the sum of k squared times the probability of taking the value k, minus the expected value of Sn, quantity squared, which, as we computed above, is going to be n over 2 squared. Now, I am not going to make any attempts to compute this combinatorially. I will tell you that it can be done, and it's a pretty fun, slick calculation using some relationships between binomial coefficients. If that's the sort of thing that you find fun, then I encourage you to go ahead and compute that the answer is n squared plus n over 4 for that first term. And so the variance turns out to be n over 4. Interestingly, each of the two terms in the variance grows quadratically with n, but their difference grows only linearly with n. And so what that means is that this upper bound on the probability of being at least epsilon away from the mean actually decays with n. So as n grows, this distribution gets more and more concentrated around the mean. And that is what the mean, or expected value, actually means. It means that in repeated trials, like repeated tossing of a coin, that's the value that the average approaches. The empirical average is a random variable, but its randomness gets damped down and it concentrates more and more around one value, the expected value. We can see that in these pictures that show the binomial distribution with different n. Here we have n equal 30, here n equal 90, here n equals 270. And we see this binomial distribution getting more and more concentrated around the mean, 1/2. Now, we saw that on the previous slide as a consequence of some calculations that you may or may not choose to do on your own. But it doesn't really have anything to do with the binomial distribution per se. The reason that this concentration comes up is because of the normalization here, the 1 over n, and the fact that in this case, the variance of Sn doesn't grow quadratically, even though the variance is a quadratic term. And that is because these are uncorrelated, as we saw last time. So that is the general theorem, which goes under the name the weak law of large numbers. Take any sequence of L2 random variables on a probability space and suppose that they are pairwise uncorrelated. That is, the covariance or correlation between any pair of distinct terms in the sequence is 0. Let's also suppose that all of those random variables have the same expected value and the same variance. Then, in that case, taking Sn to be the sum of the first n terms in the sequence, for any tolerance epsilon, the probability that the empirical average of those random variables differs by more than epsilon from the mean actually decays at the rate of at least 1 over n to 0. We get concentration about the mean in the large n limit for any sum of uncorrelated random variables with common means and variances. The proof of this is actually almost the same as the calculations we did on the last page, together with noting that the variance will always grow only linearly instead of quadratically for this sum. So why is that? Well, let's go through the proof. By our assumption, all of the random variables have the same expected value, alpha, and therefore the expected value of the sum is going to be n times that common value, alpha. And therefore the expected value of the empirical average, Sn over n, is going to be alpha. Therefore, by Chebyshev's inequality, we can estimate this probability, which is the probability that this L2 random variable minus its mean is bigger than or equal to epsilon in absolute value. That is bounded above by the variance of the empirical average divided by epsilon squared. And as we noted previously, we can pull out the 1 over n to give a 1 over n squared from the variance, and so we are left to control the variance of Sn. Well, the variance of Sn, which is the variance of the sum, x1 plus xn, as we showed last time, because these are uncorrelated, the variance of the sum is the sum of the variances. Each of those, by assumption, is t, and so this is n times t. And therefore, Chebyshev's inequality estimates this probability to be less than or equal to n times t divided by n squared over epsilon squared, which is t over n epsilon squared. And that, indeed, goes to 0 for any fixed epsilon. That is the weak law of large numbers. Now, what makes it weak? There is a strong law of large numbers, which we will get to a little later, which says that under some somewhat stronger assumptions than we have here, but still in the same spirit, we will actually have that this empirical average random variable converges almost surely to alpha. This is a weaker version of that because the kind of convergence has to do with this concentration of measure rather than actual almost sure convergence. Let's talk a little bit about that concentration of measure type convergence. What we've shown here is this concentration of measure property here. But what kind of limit is this really? It's an asymptotic concentration kind of limit. But does it mean something fundamentally different than convergence of this random variable to that constant value? Almost surely, or some other way that we're used to understanding? Well, as we mentioned a moment ago, this property actually does hold true for the empirical average under some mildly stronger assumptions. But that doesn't mean that it follows from here. In fact, it doesn't. Let's consider a related example. Suppose, as we've thought about once before, we have a sequence of coins. I hand you a coin, you toss it, and record the result. Then I hand you a new coin, you toss it, and record the result, and so on. the coins that I hand you are becoming increasingly more biased. The probability of getting heads on the nth coin is not 1/2, but 1 over n. And so the probability of getting tails is 1 minus 1 over n, which grows toward 1 as n goes to infinity. Now in this case, what can we say about the probability that the nth toss has value bigger than or equal to epsilon? Does this approach some value? Does xn concentrate about some value? Well, from here we see that the expected value of xn is 1 over n. And 1 over n tends to 0. So if we were going to see concentration here, we would expect this to concentrate around 0. Let's check to see if that happens. We could use Chebyshev's inequality, but actually we don't need to in this case, because the probability that absolute value of xn is bigger than or equal to epsilon is just the probability that either xn is bigger than or equal to epsilon or xn is less than or equal to minus epsilon. But that's not possible. Xn takes values 0 or 1 only. So this is the probability that xn is bigger than or equal to epsilon. And since epsilon is strictly greater than 0, the only way that can happen is if xn is equal to 1. And so this probability is equal to 1 over n, which indeed goes to 0. So following the same kind of scheme we had up here in the weak law of large numbers, this sequence xn converges in probability to 0. But does that mean that it converges to 0 almost surely? Well, the answer to that is no. And we'll see when we get to the Borel-Cantelli lemma part 2 that in this example, the probability that xn equals 1 infinitely often not only is not 0, but is actually 1. So this is a very false. xn does not tend to 0 with probability 1. In fact, with probability 1, it does not tend to 0. With probability 1, 1 keeps coming up infinitely often in this sequence, no matter how far out you go. Next time, we will explore this somewhat strange and weak notion of convergence in probability, a little more. Even though it is strictly weaker than almost sure convergence or other kinds of convergence that we've discussed like L1 or L2 convergence, it's actually an incredibly useful tool for understanding those stronger forms of convergence.